I'm really pleased to see this happening. I helped arrange this webinar because the low frequency part, and I don't want to steal any of Michel's material, but Crosswell strain and microseismic now go hand in hand in a lot of projects, and we've been struggling to understand what we were seeing for a long time. It's been rather entertaining, really, but I think today you'll see some things that will help you understand what you're seeing in your data, assuming you acquire that type of data, and in particular with disposable fibers, which are kind of new and exciting, at a much lower cost than traditional deployment of optic fiber. So today, Michel LeBlanc is presenting. Michel is Chief Scientific Advisor within the Sensor Physics Group at Halliburton and Team Lead for DAS Deployment Technology. He has a PhD in Aerospace Science and Engineering from the University of Toronto, where his research was in the integration of fiber optic sensors within composite material structures. His first job outside of academia was at the Naval Research Laboratory in the Fiber Optic Smart Structures Group led by Dr. Alan Kersey. He is co-author of the Fiber Grading Sensors, a 1997 Journal of Lightwave Technology paper that now has over 4,880 citations. His interaction with Halliburton and the oil and gas industry started in 1999 while he was at NRL, and restarted in a formal way when Halliburton acquired the downhole fiber-based pressure gauge business of Davidson Instruments, a startup company where Michel was a lead scientist. Within Halliburton, Michel expands his work in applied physics to include work on accelerometers, downhole fluid sampling, I'm stumbling over that word, densitometers it must be, and DAS technology. Michel, just a few rules of engagement. We prefer that you use the question and answer tab rather than typing questions into the chat. It can be overlooked. And if questions come along that seem really timely, I may, between slides, ask Michel to address them. Otherwise, we can hold them till the end. So, Michel?
Oh, well, thank you very much for the introduction, David, and also thank you for inviting me to give this talk. I also want to thank you all for attending, and then also very importantly, I want to thank my co-authors who are all with Halliburton and helped me put the paper together and get ready for this presentation.
All content presented during this webinar belongs to the authors and speakers. Presentation materials and broadcasts may not be reproduced and or distributed in any form without the permission in writing from SCG or the authors and speakers. Thank you so much, Michel, and let's share your screen so you can begin with your great presentation today, and thank you all for attending.
Okay, again, want to thank my co-authors and Halliburton for letting me present this talk. And so let's get started. So as David was explaining, what this will be about is discussing the use of distributed acoustic sensing for monitoring of hydraulic fracturing inside an observation well. And the optical fiber is in the horizontal portion of the well. And the purpose of doing this is for operators to better understand and be able to track what is happening during the treatment of their wells. So normally what would happen is you would have a pad with where a lot of wells have been drilled, and eventually they get all treated and fractured. But before fracturing a particular well, it can be used as an observation well for the monitoring of the treatment well. So the optical this observation well is not yet fracked, and the optical fiber is deployed in it, and then the treatment well is monitored using the optical fiber, and the optical fiber will be used for to detect microseismic generated from the fractures, or what's called fracture-driven interactions, which is the interaction by strain interaction between the fracture and eventually the optical fiber that's measuring that strain. And for example, a frac hit, if the fracture reaches the well, that's going to have a strong signal in the strain profile measured by the optical fiber. And eventually the observation well becomes a treatment well, and then potentially other wells are used for its monitoring. A lot of times permanent cable is attached to the casing, and so it's cemented behind casing, and that's what's used for the monitoring of either any well being treated that is in proximity to that well. And then for a permanent fiber cable, even the treatment well can be monitored during the fracture, and it's because here the coupling is very strong, and eventually we can operators use this to know where proppant is displaced, whether they get and even during production they can use the same cable to monitor production. But what we're going to be discussing today are only fibers that are only temporarily deployed in the observation well, either by a wireline or as a wireline deployment, or using disposable fiber. So the wireline is a larger cable, typically about 12 millimeter in diameter, that is deployed either using and brought all the way to the total depth of the observation well using a tractor, or pushed by fluid all the way to the toe of the well. And then for disposable fiber, which is a much less expensive way of deploying, a standard telecommunication grade optical fiber, not really protected, just very small size, 0.25 millimeter in diameter, 250 micron, will be deployed using a bobbin that's on a tool that gets pushed by fluid all the way to the toe of the well. And as it's deployed like that, it pays out. The bobbin actually contains the fiber, it's in the dart, and it will pay out that fiber with very low tension all the way as it comes down the well and is pushed all the way to the toe. So as you can see, this is a very convenient way of deploying fiber. At the surface, we have equipment to just hold the fiber in place and provide communication to the instrument. And then at the bottom of the well, there's extra fiber that remains in the dart. Typically, we don't use all of the fiber. And now we have a fiber that is sitting in the well. And very importantly for our application, we need the optical fiber to be touching the bottom of the horizontal wellbore, as shown here. And because it is the friction interaction between the optical fiber and the wellbore that is providing the strain coupling. It's the same thing for the wireline. It's also friction. But as you can imagine, normally, if anybody who studied experimental mechanics at school, when you bond a strain gauge on a piece of metal, you really have to have good adhesion. You want really good coupling because you want to measure the strain very accurately. And you know that this can only be achieved if you have a very good bond. Well, in our case, we don't have a bond at all, right? We just have frictional interaction. And one can wonder, like, why does this work at all? How can we get enough coupling? And that's the purpose of this paper, which was on covering both this wireline and disposable fiber, to actually explain the theory behind why this works. And there are two major assumptions that we're making here. One is that the optical fiber is straight along the bottom of the wellbore. It's not bent or anything, and that means that when it's deployed, you have to, the deployment mechanism needs to keep the fiber in a little bit of tension so that they can be, so that it's always straight, but not so much tension that it actually does not let it sink and touch the bottom. At the same time, we also need, a second assumption is that the density of the fiber or the cable needs to be higher than the fluid that it's in, so that it actually sinks and we can have frictional interaction. Okay, so having introduced that, and all those comes from the paper that was presented at the Hydraulic Fracturing Technology Conference of last February. We're going to be dividing the paper, the talk here, into two sections. First, we're going to consider very slow moving strain, and that's used for Crosswell strain monitoring. We're going to look at the theory and examples of that. And after this, we're going to look at the dynamic strain, which is applicable to microseismic. Again, looking at theory and examples. And the reason why we treat dynamic differently, of course, is that in this near static case, we're going to assume there is no acceleration present, and the sum of the forces are going to be equal to 0 in each element, and we're going to use that for our looking at our interaction. For dynamic strain, we're going to have to include the acceleration terms. And we'll end with a quick conclusion, and that will summarize the talk. So let's first, again, look at strain coupling. The two applications that I mentioned, right, they both involve using the optical fiber over the entire length of the lateral section. So we're going to be looking at signals over very long lengths. Those can be, those thousands of feet, so 8,000 feet, 10,000 feet of lateral, and the signals that we're going to be monitored are actually going to be involving a long section of that fiber. That's especially true for microseismic. But in terms of the signal itself, there's large differences and how long we acquire, etc. So for Crosswell strain monitoring, what is needed is we're going to be recording over hours at a time, and we're going to be collecting this data and interpreting the data over that full range, because every time for every stage that's being fractured, after some time the fracture approaches the observation well, and it can be detected. So we're monitoring for each stage 1 hour or more of data, and the strain rates are typically fairly small, of the order of 10 nanostrain every 10 seconds. And so we're going to be using 10 seconds as our unit of time, and that is kind of like historic because it was considered important to display and to have a knowledge of what was happening during the events. And 10 seconds was a good time interval to monitor the changes of strain, because DAS is a distributed acoustic sensing. When used as a low frequency DAS, it's going to provide changes of strain over a period of time. It's not used for measuring absolute strain like you would get with another type of instrument, for example, Brillouin, where it essentially is a measurement of the static profile of strain along the cable. With DAS, we're looking at changes of strain, and in fact, what the typical waterfall plot is showing strain rate. For microseismic, the events are a lot shorter. Typically, each event itself that we picked up is of the order of 1 second. So the processing and the analysis eventually that picks it all up is looks at very short periods of time, but over the entire length of the cable. A lot of times when we deploy cables, we have multiple fibers, and you would use perhaps potentially 2 DAS systems, one used for the microseismic monitoring and one used for the low frequency DAS and for the monitoring of the Crosswell strain. For dynamic strain, also the amplitude of strains are fairly small, very small, of the order of nanostrains. But here for microseismic, we look at a frequency range that is more typical of what distributed acoustic sensing is typically used for, of the order of 10 hertz to a kilohertz. So starting with the Crosswell strain monitoring application, if we look at what is seen typically during those investigations, right? This is an example that was collected with a permanent cable. So with a permanent cable, we expect very good coupling, and so we expect to be able to see things with high spatial resolution. And what the reason why spatial resolution is important is that it's important for for the operator when monitoring this data to know where the fracture has along the observation well, where the fracture has reached, right, or the position, and then potentially there can be multiple fractures. So in a stage, there's typically multiple clusters. So it's very useful to be able to see individual fractures from each one of the clusters and the time of their arrival and the time of their closures. And a lot of times, it's not just one treatment well that's being treated, but there's a zebra frac situation where there's 2 or more wells being treated in alternation. And so the observation well is actually going to be looking at potentially fractures coming from different directions or coming from different treatment wells. And so this is kind of like what can be seen here. You have a major hit, a fracture hit arriving at this location of the well at this time, and then eventually, probably because of a different well being treated, another fracture hit arrives and tends to close, accelerates the closure of the first fracture and things like that. So these are the kind of signals that are really useful for operators to analyze what was happening in the rock while they're fracturing their wells. In this on this side here, I have the diagram of the stress. Actually, this would be the axial strain in the direction of the in the horizontal direction of the in the same direction as the fiber. But if we look at the treatment well where the fracture originates, what we're showing here is an increase of that fracture. And in fact, what we're showing for the fracture is the pressure distribution. Oh, sorry, this would be the width of the fracture here. But then what we're seeing in blue and red are the state of stress of the rock, right, in the axial, what I call the axial direction. And you can imagine, because the fracture is opening, we have compression in this part here, right? And then near the tip, we have tension, high tension at the very tip of the fracture, and tensile also beyond the fracture. So I've shown here the fiber well. Here it could be further away. Imagine that this fracture is growing. Before it reaches the fiber well, what we see is an increasing strain. That we typically say it's a heart-shaped strain pattern. And eventually, when the tip arrives at the observation well, and when it does, it basically creates a large signal, and it's actually a tensile signal because the casing, where the fiber is not breaking. It's the fracture opening. The fracture opens in the rock, but the casing is bridging the fracture, so the casing itself is stretching where the fracture is located. But closer to the toe and closer to the heel, we have the zones of compression, right? And that's what we're showing here in blue. And that's basically what happens. And then eventually, when pressure is released and fracture treatment is stopped for that particular stage, we can observe the closure of that fracture. So that's kind of like the signal can be seen with a permanent cable. And now we want to be able to see the same thing with these disposable or the disposable fiber or the wireline. Okay. Notice that this is strain rate. So if we're looking at what's going to be very important for us, and you'll see the reason why in a second, is that when we have a fiber that is interacting by just friction, what the friction is going to provide a certain degree of hold for the fiber, but there is going to be a limit to the gradient of strain that can be transferred. In other words, once the gradients are too large, that's when we're going to have slippage. So we're looking at avoiding that slippage. We're going to consider, we're calculating what are the conditions required for that slippage. So what is going to be key for us is the actual strain gradient. So here, the data tells us what the strain gradient is, but in order to get that, you have to accumulate the strain. So because we had strain rate, we have to accumulate over time, and that's what this shows here. And if I look at where I had the maximum strain value for this particular data set, the one that in the previous slide, you can see that we have a gradient that has an absolute value of a magnitude of 47 microstrain per kilometer. Now, I use those units, microstrain per kilometer, because first of all, microstrain is a known value for us for strain, right? We know that metal would typically yield around what, 26 microstrain or higher. So we know that 47 microstrain is a relatively small strain when it comes to metal, at least, right? But to get an increase of strain of 47 microstrain over a length of 1 kilometer means that it's a fairly small strain gradient. And the reason, and this is key for the reason why both the wireline and the disposable fiber work, is that the gradients involved are very small. Okay, now if we have fiber slippage, right, what's going to happen is that the gradient are not going to be transferred according to what's happening in the wellbore. With slippage, it means that the strain in the cable will not be are going to be smaller, and the gradients are going to be smaller. So if we look here at the limit, right, if we start here on the upper left, we have a permanent cable, and we're assuming 100 microstrain, 100 nanostrain per 10 second strain rate. So we start here at 0 and the strain builds up, but I'm assuming I've just made this is a model, as I just look at an increase of strain over a 10-meter region of the cable, and you see here that peak of strain at the end there at the 30-minute time point. Because of permanent cable, we've got good coupling, and we've got essentially that wellbore strain is duplicated. But if we're using a flexible cable where there's a limit to that gradient, the sharp increase of strain here is actually can only grow with that maximum gradient of in this case 1500 microstrain per kilometer. So we can still reach the maximum strain, but you can see that it took some distance to do that, and the peak strain value is only occupying a small portion of the total. And then if we further limit the maximum gradient that can be achieved, then actually you get an attenuation of the strain value. You would no longer reach the maximum strain, and we got the strain gradient that is taking place over a wider range. And then if we have an even smaller gradient, then the range where this is occurring is even smaller. And the peak strain, the strain values are actually smaller, and that's why it's so dim here. Now, what I'm showing here is an example of how the friction can happen, but friction is always something that depends on the load history. And in this case, the symmetry in the pattern implies that it was just as easy for the fiber to be pulled from the heel side as from the toe side. But in reality, this may not be the case, and so you can have asymmetry. Once you have slippage, you can have more fiber being pulled from one side over the other. And for disposable in particular, where the toe, essentially no force at the very toe, there's a tendency for the slippage to show an increase of tension towards the toe, and a lot of times so even a decrease in tension towards the heel. Okay, so this was for the cumulative strain, and really I want to show actually what the image that is shown in the paper itself, which is how this would be seen in the waterfall plot of strain rate. So permanent would be the constant strain rate, and then once we start having poor coupling, we start to see this widening. Now let's see the theory for this. So the theory is actually quite simple because all we're going to do is look at an element of a cable, and we're going to just look at the horizontal forces and the horizontal displacement. So the displacement is zeta. You'll see this variable throughout this part here, and it's the displacement along the axial direction of the fiber, which is the z-axis. And for near static, we're going to assume no acceleration, right? It's static, so the acceleration is 0. So that means that the sum of the forces here is equal to 0. So that means, that our so we come up with this. They're just doing the body diagram, and that means that our friction, right, which is force per unit length, must be equal to the gradient of our force along the cable. Now, the force along the cable, that's proportional to the strain, right, via a term that we call the stretch coefficient. It's the inverse of the effective stiffness of the cable. And so so that means that our friction is going to be proportional to the gradient of strain. So this is when we have no slippage, right? But what happens is we know that the friction, what it's going to do, it's going to be as high as needed to avoid motion, relative motion, right? But at some point, there's a maximum value to it. And that maximum value, if we use Coulomb friction, is just the coefficient of friction times the weight of the cable in the fluid. This is a weight of the cable per unit length in the fluid. And so that's our maximum frictional term. So because we have a maximum frictional term, and the friction is proportional gradient, it means that our gradient has also a maximum value. And that maximum value is simply given by this, the coefficient of friction, the stretch coefficient, and the weight of the cable in the fluid. Okay, so if we look at this now and look at cables and just make some calculations, we can see what the maximum strain gradient that can be achieved for different configurations. So here I have the disposable fiber on the left and the wire line on the right. And I put here 125 micron and 80 micron as the standard size for the glass portion of the cable, of the optical fiber. The 125 micron would be typically to about 240 to 250 micron diameter with the coating. 80 micron would be a total OD of about 160 or 165 micron. You can see that either one would be providing about the same level of maximum strain gradient, about 66 microstrain per kilometer. And because 180 micron fiber is more expensive and more difficult to deal with, the standard fiber is typically what's used there, 125. There is no advantage in going to a smaller fiber. On the wireline side, that's the different examples as the paper explains. W3 here, this is our fiber log wireline. And then just to compare what other dimensions of cable would do, I've used information from the CAMISA catalog. Those are not fiber wirelines, but it's representative of what you could do with a wireline. And as you can see, even among the different dimensions for the wireline, it's also about the same maximum strain gradient, which is of the order of 200 microstrain per kilometer, better than the disposable fiber. And then all of that depends on friction. Here I made the assumption of a coefficient of friction of 0.3. It could be higher for a wireline because wireline is rougher and in contact with the metal. So this could be an underestimate of the friction. But if you can, in this particular example, we have a wireline, and I'm just using, this is from real data, and this is the cumulative strain calculated from the monitoring of that treatment stage. And if I look at the maximum strain gradient that was observed here, you can see that it's actually about 200 micro strain per kilometer, just as the theory actually predicts. This is for the cumulative strain, and this is not what we normally look at, right? What we normally look at is the strain rate. And it turns out that for a wireline, we're very lucky about one thing about how the slipping happens. It happens in a very very sudden bursts. So if I look here at the general profile, you can see the heart shape, right? Strain pattern arriving and the fracture hit. But going back here, you can see that I have better spatial resolution than could be seen from the cumulative strain, right? So in other words, when I accumulated the strain, I lost some information that I can see here. And the reason for this is that there is slippage that occurs, but the slippage is very sudden, and most of the time there is no slippage. We're in stick mode. So imagine slick and slip and stick. Slip is bad, stick is good. So we have in the background the higher spatial resolution that we want, and then we have the slippage events. And you can notice these slippage events, what they correspond to is a readjusting of the tension along the wireline. So you're pulling from one direction, so you're reducing the tension in this part here and increasing the tension in there because it's being pulled from, in this case, towards more predominantly towards the toe is where the cable is coming from, but not exclusively, as you can see here. We also get some motion in the opposite direction. So once these readjustments are made, in between, we got a time of where we can use we have a good correspondence between the strain rate in the wellbore and the strain rate measured by the cable. And because of the nature of these sudden slip events, we can actually filter them out. And once they're filtered, you can see the image is a lot closer to what we would expect to get from with a permanent cable. Okay, now let's look at disposable fiber. And with disposable fiber, we can have slippage, and this is definitely an example where we have slippage. When you see the strain pattern when it arrives, there is still where we can identify a hit, right? So the timing of the arrival and even the position along the well is pretty clear, but there are a lot of it that is kind of lost from the effect of that slippage, and even in the low strain portion. And presumably what's going on here is that we'd have poor coupling, the fiber is suspended, floating, and results in the slippage, but the slips are not as sudden as for the wireline. And you can see here that we got this kind of like blue on the one side and red on the other. We had the slip, the readjustment of the fiber position is taking place at several spots. So this is undesirable. We would like to avoid this. And but lucky for us, just as we do this, right, to confirm what's happening, when we do the cumulative strain, when we accumulate the strain, we get this kind of strain profile, and then we can look at the value of the strain gradient here, and you can see on average between here and here, it's actually quite low, about 15 micro strain per kilometer. It's even lower than predicted. Mind you, maybe this is the better place to get the gradient, where it would be closer to that 60 value. But it's a small value, and it's we would definitely want to be able to achieve more than that. And that's where the design of the disposable fiber with grease on it. The optical fiber, as it's being pulled out, it's embedded in a layer of grease, and that grease, under the right condition, when it's deployed, it provides a better contact, between the optical fiber and the bottom of the wellbore. And when we have that, we have very good coupling. And you can see here there are 3 fractures arriving almost at the same time. We can see the strain shadow of one on the other here. When this one begins, it kind of closes the other one temporarily. All this is really good information, good data, and it's obtained with a disposable fiber. And if we look at the cumulative strain and looking at where we had the maximum strain values, maximum strain gradient, it's a very large strain gradient compared to what we would expect if friction alone was responsible for the coupling. So here we can see that the adhesion of the grease with the Wellbore has really helped with the coupling. Okay. And so one thing we want to do is to always make sure that we would like to improve the coupling, and what can be done, of course, is to look at the theory and determine like what can be done in order to optimize our cable to make this work better. So if we want to increase this value, at least the one by friction alone, we should try to aim for a high density over stiffness ratio of the cable, because yes, we want the cable to be heavier so that it sinks and has good frictional contact with the Wellbore, but we don't want that at the expense of the stiffness, because the stiffness is what will prevent the strain from happening in the cable. So the ratio of density over stiffness is what we want to optimize. We want that value to be high. Okay, now we can move on to dynamic strain. Showing you here an example again of dynamic strain of a microseismic event picked up by a permanent cable. You see that it happens, we're monitoring a long portion of the Wellbore. The timing, this is a total of 1 second here. We have the arrival of the P wave that travels faster being detected first. And then the shear wave, and then from the pattern, we know that the origin of that microseismic event was a line perpendicular to that depth there along the observation well. And if we look at the maximum strain values, the amplitude of that strain, they're small. That's what we're noticing here, and that's going to be important there for the rest of the in how these behave in the well. So let's look at the theory for this again. We have our element, and remember zeta is our axial displacement. We have a relationship between the force and the strain along the cable. We have again that we can apply Newton's second law, but in this case, total force is not zero. We have to keep the acceleration term, the mass times acceleration, so doing that, right? Just expanding this, the total force is the gradient of force, and then the role of friction, and then our acceleration is that dm here, taken as the dz times the weight of the cable divided by the gravity constant, and then our acceleration. So that means that in our case, in this case, right, to avoid slippage, we would need the friction to be equal to the strain gradient and a term that is proportional to the acceleration. But we still have Coulomb friction, and so, sorry, there's still a maximum to that friction, which is the coefficient of friction and the weight of the cable per unit length in the fluid. Okay, so how we're going to deal with that acceleration term? Well, the thing to do is we know that we don't want slippage. So let's assume we do not have slippage. Okay, let's assume that the friction term is large enough to avoid slippage, and let's assume that we have a wave traveling along the Wellbore with this pattern of displacement. So this wave, how is it there? Well, it has a wavelength of lambda size here and c size. These are the apparent wavelength and the apparent velocity of the wave along the Wellbore. And what I mean by apparent is that in the rock, there might be a P wave or S wave traveling at its particular speed. And here I'm just looking at one wave, right? One infinite wave. And we have a relation between the wavelength in the rock and the speed of the wave in the rock, and the apparent ones along the direction of the Wellbore, and that's in relation with that angle there. When theta equals 90 degree, you essentially have infinite apparent velocity because the Wellbore sees all of the event at the same time, right? The wavefront hits the entire Wellbore at once. Okay, so having done that, right, having made this assumption, then I can calculate the strain, which is the derivative of that displacement with the z by z, and that gives me this, right? And then that gives me here my amplitude of strain. And I have this so I can also replace the acceleration term, right? So what we know is that clearly the frictional term is going to be proportional to something that is has an amplitude of epsilon 0, and since my maximum friction value, right, is given by this, I can replace that in here and obtain a relation between that gives me my the maximum value for my amplitude. So what this says is that friction can allow us to have this profile of the displacement along the Wellbore, as long as the amplitude of the strain is not higher than this value here. And this is, again, we have our coefficient of friction and our weight of the cable in the Wellbore, which that's what we expect, right? And then there is now a denominator where we have the frequency, so there's a 1 over f dependence, which is also not surprising. And then there's this term here that includes the property of the cable, the stiffness of the cable, the weight of the cable, and then the apparent wave speed. And because of the sign difference, we know that this value can actually reach 0. And this is an interesting resonance feature, right? It's a resonance that is not a function of frequency, but is a function of the wave speed. And it's when the wave speed is equal to the speed of sound of the in the cable, right? A disturbance, how fast is that going to propagate along the cable? If it's the same as the apparent wave speed, then we basically are saying that epsilon naught is maximum. It's at infinite. There is no impedance. There's no blocking of that there's no slippage, because essentially there's no force required for to propagate that wave in the cable as relative to the Wellbore. So that's kind of like what we see here, and we have here in blue we have the optical fiber, the disposable fibers, and in orange we have the wireline cables. And you can see different fibers or different cables have different specific resonances here, right? But my axis is the apparent wave speed, and then on this axis we have the amplitude of strain. Now remember that we were seeing very low amplitudes, right, in the nanostrain region. So these are fairly high values compared to the maximum values of amplitudes that we see in the data in the field. So what that means is that if these values were higher than this, we would have slippage, and when they're lower, below the curve, right, when we're below the curve, there is no slippage. So what it tells us is that both the wireline and the disposable fibers will transfer strain, the strain seen in the Wellbore without slippage, because friction is strong enough. Here we have the dependence now with frequency. So if I select one particular apparent wave velocity, we've got this 1 over f dependence, and we have the wireline. You see the wireline is better, like it can sustain higher amplitudes before slippage than the disposable fiber. But both of them are above what we normally see in our data. So that's the reason why both of them are expected to work well. And in fact, that's what we observe in the field. So already here, I'm just showing an example with disposable fiber sitting at the bottom of the horizontal wellbore. And you can see a microseismic event with the P wave and the S wave arriving. And we can definitely see that pattern, and we can properly interpret this, this data. Now, it's not perfect, right? It's not without any noise. Sorry. What we see is these bands here, and it's very likely that what this represent is positions along the wellbore where the optical fiber is not resting at the bottom and not touching. It could be floating, suspended, could have not as good of an interaction there. And so there are these definitely these places where we have less good coupling. But because of the type of patterns we're seeing, and they occupy such a long total length of the wellbore, we're able to deal with those noise patterns, and they're not affecting our ability to detect those microseismic events. Now, we expect a wireline to be better, and in fact, that's typically what we see as well with the wireline. But you can see here a very clean signal with the wireline. That would be just as that is no different from what a permanent cable would have detected. We have good coupling for microseismic. So I think the main conclusion we can say is that both for Crosswell strain monitoring and for microseismic, we have amplitudes of signals that are of strain signals that are small and gradients that are small, so that friction can be strong enough to provide good coupling, and a lot of that has to do with the fact that we're dealing with very long interaction lengths, right, of the optical fiber. So we need that the fiber need to be resting at the bottom of this and touching the well. And in some cases, for the disposable fiber, that's not the case if it's suspended. But well, we can certainly see that in most of the time it is good. And there's some thresholds for slippage that must not be exceeded. That kind of threshold is pretty much always satisfied for microseismic, right? We're never exceeding that. So both cable types, both flexible cable types work well. For Crosswell strain monitoring, a lot of times there would be a possibility there is possibility for the disposable fiber to slip, or even the wireline to slip, but the impact on slippage is different. For the wireline, because the slips are sudden, we can essentially filter them out, and we still have pretty good resolution. And for the disposable fiber, with the grease present, we can achieve adhesion, which actually helps with that coupling. So that's all I have. I certainly, again, thank you for attending, and I'm open for questions. I also thank, of course, our management for letting us publish this work.
Michel, can you read the questions? Can you see the questions?
Let me see.
Because
Okay, I just have to bring my question and answer. Okay. Sam.
I'd be happy to read them to you, but if you can read them.
Okay, no, I can read them.
Some of them are a bit orthogonal to the topic, frankly, but I'll let you decide.
Any deployment of fiber in coil tubing for Crosswell monitoring, Crosswell frag monitoring. If friction is the way I have. Okay, so let me address the first part about coil tubing. It was important that I referred to this as flexible cables, and the reason for this is that it's important that bending does not really play a role in the interaction, right? And so flexible means that it doesn't take much. The bending moments are not strong, and it's easy to keep the fiber or the cable straight. When it comes to a coil tubing, this doesn't really apply. So I think it's possible that you could get some good interaction and some good signals, but the theory that I was giving here is probably not applicable, because it really does not take into account the effect, the bending moments that are required. And a lot of times, a lot of the forces or displacements that are going to be happening are just, instead of creating strain in the cable that would be in the coil tubing, it would simply straighten the coil tubing and not be used for, and we would not be able to detect that. Second question from Aldo here. Are you using different equipment, Integrator, for low frequency DAS strain rate and high frequency strain rate measurement? Thanks. Actually, it's the same instrument. All we are doing is using, when it comes low frequency DAS, we're still collecting at the same high frequency rate, but we're just accumulating the strain changes up to, like, let's say a given interval, which could be 10 seconds or could be smaller or could be higher, but it's, and then it gets displayed on the waterfall plot like that. So it is the same instrument. It's just the processing that's slightly different. How is the fluid pressure within the casing accounted for in the friction calculation? It's a good question to talk about the fluid pressure. One thing that is actually not accounted for in the paper, but I subsequently did, was to include the effect of friction on the diameter of the fiber. Like, that's especially relevant for the disposable fiber because the coating is going to compress. And actually that has a beneficial effect because it actually increases the density of the fiber, right, and without increasing its stiffness. So it actually improves the maximum gradient that can be achieved. It's actually a desirable thing. So that's for, like, just a static pressure. And then dynamic pressure, right, when we have a microseismic event or something and changes the pressure field inside, well, that signal is in phase with the strain signal, first of all. And then secondly, my calculations are that it's actually corresponds to a small portion of, like, the total signal. It might be responsible for about 5% of the signal strength. So we can actually ignore that effect for what we're doing here. Brian has a question here. In terms of fiber in metal tubes, what's the role of excess fiber length for static and dynamic strain coupling? Do we need to exceed or to localize EFL to resolve strain? That's an absolute excellent question, Brian. That's definitely a question that we had to ask ourselves. And in the paper and throughout the presentation, I always talked about the strain of the cable itself. So the wireline moves or the permanent cable moves, but there's definitely at some point, right, there's an optical fiber in there, and that the coupling between that cable, that fiber, and the rest of the cable is important. I mentioned some of that in the paper. There is essentially a factor that can take into account the helical aspect, especially for the wireline, but even for when we have extra fiber length, that means that in the metal tube, we put more fiber than the length of the tube, so that when the tube expands with thermal expansion, the optical fiber is not placed under high static strain. Okay, and if it's like that, if it's so loose, then why do we get coupling? Well, it turns out that the gel that is used, SEPI gel, that gel has a yield point, and that yield point is actually quite high. I'm going to be talking more about this when I present next month at the San Antonio workshop, but that gel provides enough coupling to achieve large gradients of the order of 20,000 microstrain per kilometer. So it's not a limitation. And it just turns out that because of the properties of the gel, we're still able to get good coupling. So certainly is the case for microseismic, right? And then, but even for the Crosswell strain monitoring that happens slowly, the gel, it provides enough viscous force that there is that the cable is still the strain changed seen by the cable is transferred to the optical fiber. Next is, have you modeled how much deviation is necessary for coupling? No, I think what you mean here is the angle. The theory is for 90 degree, or completely horizontal. But if you had a different angle, I think what would be equivalent to having a lower coefficient of friction. Maybe like you can basically, it could be taken into account as a just a reduced amount of friction. But there might also be the issue that there was a greater tendency for gravity to pull in one direction. So yeah, that could be an expansion of the work to try to understand how that would work. So good question. Let's see here. So Professor Jen here have you seen in the field data that the grease fails to provide coupling for disposable fiber? If so, what could be the reason? Absolutely. I think if I said that no, we haven't seen that, and anybody from our operator who have actually seen disposable data, they would quickly correct me, right? We have the grease is effective in some cases, and in a lot of cases it's not. And when it's not, then we're still able to use the disposable fiber data, but there's some things that are not revealed anymore, like because of the loss of the spatial resolution. So what can be done to improve that? Well, this is something where we have been trying to understand the reason why we get good coupling and why not, and a lot of that has to do with the deployment itself, right, and how fast you deploy the tool, and then potentially also how stable the fluid is in the wellbore while this is happening and then afterwards. So we're doing as much as we can to improve our cable. I mentioned some of the ideas before, and we think that as we improve the ability of the cable to sink down and things like that, that it will help with the grease effectiveness, and we can increase our percentage of wells with disposable fiber where we have exceptional quality, like the example I gave earlier. Are pulley coupled fiber locations stationary throughout the monitoring program? Yes, usually that's the case. Although I have to say sometimes, especially for the disposable fiber, but even for the wireline, you can have very sudden shift of the entire fiber. When we deploy this fiber, the disposable fiber, it's the very end of the fiber where it's being paid out. Excuse me. Comes out from a point at very low tension, but there's fluid flow, and that flow, which is low viscosity, that's friction reducer in the water, but it's still there's enough friction there because it happens over a very long length to cause some tension in the fiber. So as we go around the horizontal, there is tension in the vertical section typically, and then also even in the horizontal section. So it can happen that that a sudden shift of the release of that tension happens, and we would then see a signal over the entire length of the fiber. And then after that happens, a lot of times, there's the fiber, the locations where the poor coupling are present. Those locations may have moved. Okay. Next one. To simplify deployment and field back of the envelope calculations, is there a way to know the minimum moment magnitude the fiber would be able to detect approximately? I'd have to get back to you on that. My colleague Henry Bland might have those values. I personally would not be able to answer that at the moment. So if you send us an email, I have my email present there. I'll just make sure it's there. There we go. I will be maybe able to provide an answer. And next question, Professor Jun, do you think the liquid gel may relax strain over long term, even before the yield point? That's an excellent question. you would think that that would happen, and it certainly. Short answer is that we've not seen that happen during the length of the stages for Crosswell strain monitoring, but that is just a few days, right? And it's quite possible that we have competing rates. Like when we deal with strain rate, you would have increase in tension and decrease in tension, etc. It's possible that there is a small kind of, I would call it slippage happening at this that is simultaneous, right? So that the relaxation may be present, but it's kind of hidden by the fact that things are changing and we're still able to monitor. So how much of that is really happening, I actually don't know, but it's possible. What I can say is that it was surprising, and I'm gonna present that in August, is that you would expect this viscosity to go down and the yield for more of a tendency for easily losing that coupling with higher temperature, and it turns out it doesn't happen. Higher temperature, we still have a good preservation of that shear stress provided by the gel. Next one, slide 27. Is it possible that the horizontal strips are common mode noise because of the instability of laser? 27. I don't. I actually don't think so. I mean, the laser pulses are traveling over the entire length of the wellbore and come back. And why would they be occurring only at like a specific depths, right? These are all the same. These are the same points of the fiber, and involves thousands and thousands of pulses of the laser. So no, I don't think this is. These are common mode effects like that. Okay, I see there's no more questions.
There were a few in the chat that didn't make it into the question and answer panel, so if people want to correct that, then maybe we could take a shot. Looks like another one just came in from Matt Lawrence.
Okay, here's one. In cases where we've deployed multiple single-use fiber darts in the same well due to breakage, okay, the horizontal bands stayed at exactly the same depths, okay. These horizontal bands occur more often during pumping operations and seem to blend into the background when the frac pumps cease operation. Wow, that's an excellent observation, and that would kind of like go in line with what we think is happening. That there's two high points, and in between the fiber can be suspended. And of course, if you pump another cable in there, the same high points are going to stay there. They're part of the well, and the same locations would have the same features, right? So thank you for sharing that with us.
All right, well, that was very good, and thank you very much, Michel. And thank you, everyone, for attending. And we'll look forward to your next paper.